Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at absolute convergence of a series. And last time we discussed what is called a positive term series. So these are just those series where you have each term non-negative. So as we mentioned, it should really be called a non-negative term series, but this is the standard usage. Okay, so now suppose we have a positive term series, then we saw that the sum of the series can be written as, or rather it is equal to the supremum of the sequence of partial sums. So this is nothing but the sum of the first n elements. And if you take the supremum, that is the sum of the series. This could be infinite. So that is when the series diverges, and if this is finite, then the series converges, and this thing is actually also equal to that thing, which was something we saw, and it's easy to prove. All right. So again, so suppose now we have some arbitrary series, then we defined a rearrangement of that series as any series of this form, where sigma is a bijection of n with n. So it's kind of a permutation. In fact, it's exactly a permutation of n, and all you've done is basically permuted the summands and obtained another series. So that's called a rearrangement. And we saw that if we have a positive term series, then any rearrangement of, okay, so if we have a convergent positive term series, then any rearrangement is also convergent and with the same sum. And if a given positive term series is not convergent, then any rearranged series is also not convergent, and well, even then this equality holds with the understanding that if this is infinite, then that means that this diverges. All right, so this is what we saw, and now let us go to what we want to discuss today. So okay, so we have some series, and we say that it is absolutely convergent if well, okay, so if this thing is convergent. So meaning the series with the summands replaced by their absolute values is convergent. This is where this term is coming from. So you pick a series and form the series of the summands with absolute values. And if that is convergent, then we call the original series is absolutely convergent. Okay, and here is a very simple lemma, is that suppose we have a absolutely convergent series, then the series is convergent, meaning every absolutely convergent series is convergent. And in fact, the sum of an absolutely convergent series is dominated in the absolute value by the series formed by replacing the summands with their absolute values. So okay, so let's see how to do this. So proof is just Cauchy's criterion. So what we have is, let epsilon greater than 0, then there is n such that this guy such that whenever m and n exceed capital N, we have this thing is less than epsilon. So all we've used is that this thing is absolutely convergent and Cauchy's criterion. Okay, and of course we can drop these absolute values, doesn't matter, but let's put them. So this implies in particular that, just using triangle inequality, this is also less than epsilon, and that's it. So this implies that the series is convergent. By Cauchy's criterion, And the second part is something I leave as an exercise. So this I leave as an exercise. Okay. All right. So any absolutely convergent series is convergent. So here is a piece of notation which I thought I will use, but probably not. But here is the notation that for any natural number n, we write bracket n to mean this set, the set of first n natural numbers. Probably I will not even use this. Okay, so here is a very simple lemma which I won't prove. Is that suppose we have a bijection of natural numbers with natural numbers, and n is any positive integer, and n is any natural number, that is. So then we want to say that there is some natural number p such that this, which in above notation can be written in this fashion, is contained there, which in the above notation can be written in this fashion. So okay, so let me also emphasize what this is doing. Basically, you have applied sigma to every element of that thing to obtain this set, and therefore I'm writing it this way. This is also just a notation, and a good one. Once you have fixed this notation, this is a good notation. So all we are saying is that if we have a bijection of the naturals with naturals, then for any positive integer n, there is some other positive integer such that the first n positive integers is contained in the sigma image of the first p positive integers. And this is nothing, this is very simple. Okay, so now let us go to the main theorem of today's lecture, is that suppose we start with an absolutely convergent series, then every rearrangement of the given series is also absolutely convergent with the same sum. So this is exactly what we saw for positive term series. A positive term series is of course absolutely convergent. A convergent positive term series is obviously absolutely convergent. Because everything is already positive, so putting absolute values doesn't, everything is already non-negative, so putting absolute values doesn't change anything. So this is a generalization of that fact. Now we are not insisting that this is a positive term series, we are just having an absolutely convergent series. And we want to show that every rearrangement is convergent with the same sum. Every rearrangement is in fact absolutely convergent with the same sum. Okay. So fine, so let's do this. So we have an absolutely convergent series, so we already have this thing is finite. So we have that. And let sigma be any bijection. So then we want to show that this series is absolutely convergent with the same sum as the original one. So this makes sense because since our series is absolutely convergent, this series is convergent and therefore this is a real number. So this makes sense, and what we want to show is that this is also absolutely convergent, so this sum makes sense. In fact, these two things are equal. Okay, so this is what we want to show. So first let us show absolute convergence. Note that we have this is equal to this because this is a positive term series, because is a PTS, and this guy is a rearrangement of the original guy. So this is where we use the previous lecture. So this is a positive term series, and clearly this is a rearrangement of it. So this sum is equal to that sum. And since this is finite, that is also finite, and therefore the absolute convergence of this guy has been established. So we have, this is absolutely convergent, and now the main task is to show that. All right, so what we want to show now is the second part. Let me highlight that. So we want to show that this is equal to that. Now this is what remains. Okay, so let me write this equal to Bn. A sigma n has been written as Bn, and now let us define the partial sum. So let Sn be equal to this, the partial sum of the first series, and Tn is equal to the partial sum of the second series. Okay, and say, and let Sn converge to S. We know Sn converges because the series is convergent, and Tn converges to T, and again we know that this thing converges because this series is convergent, as we have already shown. Okay, so to do this thing, let epsilon greater than 0 and we will show which color should I use, let's say orange. We will show that there is a P such that whenever little n is greater than or equal to P, we have this is less than epsilon. Okay, so this will show that actually S is equal to T, and that is what we want to show. So this is what remains now, the orange thing. All right, so now we begin. So by Cauchy's criterion, we have fixed an epsilon greater than 0, and now we have by Cauchy some positive integer such that whenever n and m exceed that thing, we have by absolute convergence of the first series, this is less than epsilon by 2, I will write. Okay, and now we use that previous lemma thing. So let P be such that the first n integers is contained in the sigma image of the first P integers. So even though I introduced this notation, let me expand on it. What I'm writing is this. This is what I've written in the above line. Okay. So then, for little n exceeding little p, we have Tn minus Sn equals, just substituting, which is equal to Again, this is just substitution again. And now for the key step. So this thing is sigma. Okay, let me break this down into two steps. So let me write it as k in this set sigma k minus k in this set ak. And now here is the key step. So this is equal to sum k in little n, and I'll take away something which I have to explain. So I'll take away this thing. Minus I'll take away this thing from here. So what have I done? So when little k runs over these things, over this set, where again, what is that set? This set is nothing but, this set is sigma inverse 1 dot 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 sigma inverse capital N, if that is visible. Okay, so when little k runs over this set, a sigma k runs over a1 up to an. So that's exactly what you get when you run little k over this set. And when you run little k over this set, again you get the same thing, you get a1 up to an. So we have just cancelled out that part. So in this difference, we have cancelled out that part. So here we take the correct indices and here we take away the correct indices. That's all. So it's nothing mysterious. So this thing is equal to, okay, so we are really interested in the difference. I mean, I want to estimate the difference of the absolute value. So that implies Tn minus Sn, absolute value, is equal to the absolute value of the above thing. Okay. And now we estimate. So this is at most, by triangle inequality, this is at most summation k in that plus summation k in that thing. Right. And now this is again less than equal to, so this is actually another estimate. So what happened? So here, what are the indices that we are not seeing? We are not seeing in index 1, I mean, when you talk about sigma k. So as k runs over this, you don't see the index 1, you don't see the index 2, and you don't see the index n. You see some other indices, you see something else. Those first n indices you don't see. So this sum is of course dominated by that guy. We are just, except for those particular indices, we have taken everything. And similarly here we don't see those a1 up to an things, meaning the first n indices don't occur. So we just dominated by that guy, but by what we have written here, this epsilon by 2 estimate, this thing means that this infinite sum is less than equal to epsilon by 2 plus epsilon by 2, which is equal to epsilon. So we end up showing, well, not exactly the orange thing, but we have shown this. It's less than equal to. It doesn't matter. It's the same, exact same statement. It just looks different. So basically, whenever little n exceeds p, and where did we use it? We used it because, this thing is then becomes a subset of that thing. When little n is exceeding capital N, little p, then this thing becomes a subset of that thing. Right? So this is where we use the fact that for all little n greater than equal to little p, we have this estimate. So that's it. So it looks a bit complicated, but it's not. It's really just an exercise once you know the basics of positive term series and whatnot. Okay, so that's it. That proves that every absolutely convergent series has the property that every rearrangement of it is also convergent with the same sum. And that's very nice. It is not true if you drop this hypothesis. So you can have, as we saw last time, we saw a non-positive term series with where rearrangement of it did not converge even though the original series converged. So it is not true without this assumption. Okay. So this is all that I wanted to discuss in this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.